we have the normal distribution. We find that normal distribution is mainly important. In statistics, it's used in the approximation of binomial distribution and the Poisson distribution. The PDF mass function of normal distribution for x is equal to 1 over 2 square root of 1 over sigma, that is standard deviation, square root of 2 pi times e raised to negative x minus mu squared divided by 2 variance for negative x, negative infinity less than x less than infinity. So you find that in normal distribution, the f of x is difficult to integrate, since when you want to find the area, for example, find the area between a and b, that is a less than x less than b. Let's have the sketch. So let's you should notice that normal distribution is bell-shaped, and the maximum point is always 1 over standard deviation square root of 2 pi, and it runs from negative infinity to infinity. So to find the area between a and b, we should always integrate. We integrate, but integrating this function is difficult and tedious. That's why we introduce the use of tables. We use now tables. Use tables. Tables give us the area under the curve as well as the particular value of z known as phi z. For example, you can be told to find the probability that z is less than 0.5. Z less than 0.5, when you have the sketch, you have 0.5 is somewhere here. Z less than 0.5, meaning they need the area to the left. Finding the area to the left, Z less than 0.5 is the same as phi of 0.5. So here we have phi 0.5. Now using our table, the standard normal table, we look for 0.5, which is 0.69147. 0.69146. So this is the area of z less than 0.5. What of if we add probability that z is greater than 0.5? Z greater than 0.5. Z greater than 0.5. In this one, when we draw the sketch, it's 0.5 is here. They need greater than 0.5. Greater than 0.5. We need the area to the right. So to find the area to the right, we find that this distribution is symmetrical, and when we use our table, it gives us the area to the left, but they want the area greater than. So we use our table to give us the area to the left, but since we need the area to the right, we'll take 1 minus phi 0.5. Phi 0.5 is the area to the left. Since phi 0.5 is 0.69146, it will be now 1 minus 0.69146. We will take 1 minus that one. 1 minus 0.69146 146. We have 0.30, 0.30854. So this is our probability that Z is greater than 0.5. What of if we are finding probabilities involving negative values? We are told, for example, find the probability that Z is less than negative A. Z less than negative A. It's 0, negative A is somewhere here. Less than, meaning let's have probability of Z greater than A. Now we realize that since the normal distribution is symmetrical, the probability of Z less than negative A is the same as the probability of Z greater than negative A. The area from negative A to the left is the same as the area from positive A to the right because of the property of symmetrical. So when you have probability that Z is less than negative A, it's also the same as probability of Z greater than A. Probability of Z greater than A is always 1 minus phi of A. What if we had probability that Z is greater than negative A? Let's draw the sketch. Let's have negative A. Z is greater than, which means they need the area to the right. Let's have the sketch of probability that Z is less than positive A. Positive A less than the area to the left. So here we also realize, because of the property of symmetrical, the probability of Z greater than negative A is also the same as the probability of Z less than A. Since the area from negative A to positive infinity is the same as the area from positive A to negative infinity. Therefore, the probability that Z is greater than negative A is also the same as probability that Z is less than A, which is equal to phi of A. Let us have some examples. Let's say you find the probability that Z is less than negative 0.5. Z less than negative 0.5, because of the property of symmetrical, is also the same as probability that Z is greater than 0.5. Let's draw the sketch. .5 is here. They need greater than. They need this area. Since in our table it will give us the area to the right, the area to the left, which will just phi 0.5, and they need the area to the right. Since the total area that we have, the normal distribution is 1, so we'll have 1 minus phi 0.5. Therefore, our probability should be 1 minus phi 0.5. From our table, we find that 0.5 is 69146. So we have 1 minus 0.69146. 69146. 1 minus that is equal to 0.300854. Hope it's clear. Now we are still using tables. There's some important identities that we should know that will help us to find the probability. That's the area under the curve. Still using tables. Let's say find the probability that A is less than Z less than B for A less than B and B greater than A is greater than 0, B is also greater than 0. Let's have the sketch. So A is greater than 0, that's somewhere here. B is also greater than 0 and B is greater than A. So they need the area under the curve. To find the area under the curve, we need to find phi of B, which will give us the area from B to negative infinity, subtract minus phi of A, which will give us the area from A to negative infinity. So this one, probability that A is less than Z, less than B, is the same as phi of B minus phi of A. For example, we have the probability that we have 0.6 is less than Z less than 0.91. This one is the same as, this is our A, this is our B. So this is the same as phi of B, which is phi of 0.91 minus phi of 0.6. 0.91, phi 0.91 from our table is 0.81859 minus phi of 0.6 is 0.72575. When you subtract 0.81859 minus 0.72575, we find that the probability is equal to 0.09284. So really that when you know this identity, you can work it quickly. Let us look for another identity. Let's look for another identity. Let's say now we have got probability that negative A is less than Z, less than positive B, where negative A is less than 0, B is greater than 0. So when we draw the sketch, we have 0, negative A, B. They need the area under the curve. To find the area under the curve, we find the area from B to negative infinity minus the area from negative infinity, from negative A to negative infinity. That is phi of B, which will give us the area to the left, minus phi of negative A, which will give us the area to the left. So the probability that negative A is less than Z less than B is equal to phi of B minus phi of negative A. We realize that phi of negative A, due to the property of symmetrical that we learned, is the same as, so we have phi of B minus, in bracket, phi of negative A is the same as, phi of negative A is the same as 1 minus phi A. So we have phi B minus 1 plus phi A. So we have phi B plus phi A minus 1. This is the identity. Let's have an example. Find the probability that negative 1.72 is less than Z less than is 2.5. This is our A, this is our B. This is the same as phi B plus phi A minus 1. So we have phi B, which is 2.5, plus phi A, which is 1.72 minus 1. Phi of 2.5 from our table, 2.5 is 0.99379, 0.99379 plus phi of 1.72. 1.72 is 0.95728. 0.95728 minus 1. So we have 0.99379 plus 0.95728 minus 1. Find that it's equal to 0.95107. That's our answer. You realize that you know the identity, just work it out quickly. Now let's look for another identity. Let's look for another identity. Let's say all are negative. Let's say we have all of them are negative. Negative probability of negative A less than Z less than negative B. Where negative A, where that we find that negative A is greater than negative A. Let's have the sketch. We have negative A, negative B. They need area. To find the area under the curve, we need to find phi of negative B, which will give us the area to the left, minus phi of negative A, which will give us the area to the left. So here we have probability that negative A is less than Z, less than negative B, is equal to phi of negative B minus phi of negative A. We find that due to the symmetrical property, phi of negative B is the same as 1 minus phi B. Also, phi of negative a is so the same as 1 minus phi a. So, we find that this one is 1 minus phi b minus 1 plus phi a. Find that 1 minus 1 is 0. So we have phi a minus phi b. Let's have an example. Find the probability that negative 2.65 is less than z, which is less than 1.62. This one is our A, this is our B. Using this one is negative, all of them are negative. So it will be phi of A minus phi of B. So we have phi of 2.65 minus phi of 1.62. From our table we have phi of 2.65 is 0.99461 minus phi of 1.62 is 0.94738. 0.94738. Then we subtract 0.99461 minus 0.94738. Find that it's equal to 0.04723. Find that when you know the identity, it is easier to solve. Lastly, last identity. Last identity. Let's say find the probability that z, the definite of z, is less than a. When we expand this, it's the same as probability that negative a is less than z, which is less than positive a. When you draw the sketch, they need the area under the curve, which means we find the area from positive a to negative infinity minus the area from negative a to negative infinity will give us the area in between. So this is not the probability that negative a is less than z, less than positive a, is the same as phi of a minus phi of negative a. Due to the symmetrical, because of the symmetrical property, phi of negative a is the same as 1 minus phi a. So you have phi a minus in bracket 1 minus phi a. Therefore we have phi a minus 1 plus phi a. Phi a plus phi a is 2. Phi a minus 1. Example, let's say we have found the probability of negative 0.5 less than z less than 0.5. Using the identity, we have 2 phi 0.5 minus 1. And that 0.5 is so we have 2 times 0.69146 minus 1. So we have 2 times 0.69146 minus 1, which is equal to 0.382946. 2. That's our probability. So, in our next class, we'll learn about applying the standardization, whereby we standardize so that the mean can be 0 and the variance can be 1. When variance is 1, it means the standard deviation is also 1. So in our next class, we'll see how we apply them in a real life situation. So subscribe, like, and share. Till we meet in our next class. Thank you.